Hi, it's Mr. V, and this is for Algebra 2 Honors Summer School. This is the lecture for day 13, and we're in the last week of our summer school experience, and there's a lot to talk about, so I thought I'd break this up into the notes parts, and on a separate video, do some example problems. And I could read through this. I'm going to let you do a lot of the reading, but I just wanted to point out to you, we have a lot of different ways of talking about where the graph of a parabola will cross the x-axis. One of them is with the x-intercepts. We call it the zeros, or we might call it the solutions when you set it equal to zero, or when you call about the roots, looking at the factors. So a lot of ways, sometimes they're used, I use them interchangeably, some people use them interchangeably, but they really do have a different meaning. In our talk about polynomials, what we're looking for is the solutions. And there's a lot of ways of doing that. One of the ways to do that is to use our quadratic techniques. So for example, if you could get it into the form, if you could rewrite this polynomial that's in larger than x squared into the form of a quadratic, then you could solve it. This first example is when we take the x to the fourth, and you have an x to x cubed. You could rewrite that by substituting. And this is one of those things that we want to pay particular attention to, because often you can substitute in something and make it something easier that you can deal with. Here you'll solve for u and then plug u in to solve for x squared. And this is a difference of two squares. 16 is a perfect square. 625, that's 25 squared. And so we could substitute x cubed for u, and then we end up with a difference of squares, which could be factored. This one is not able to be factored because you have an x squared here. And if you take if you substitute in x squared for u, well, you're not going to rewrite this as u squared, or if you write x to the fourth, you're not going to be able to substitute in. So you want to look at that middle term, make sure that it works. Here we have one that is weird, strange. It's got a fraction or a rational number for the exponent. If you squared both sides or wrote it like this, then you would have u squared. So different ways of writing the same thing using quadratic techniques. And here's some examples. In this one, I've got an x to the fourth and I've got an x squared. If I wrote using x squared, then I could write this as a quadratic, factor it, and then solve for it. And this is also the difference of squares twice. So I could actually factor this twice more when I'm substituting back the u is x squared. Here we have, and does this make sense to you that you would have four roots? You could have four real roots, and it does cross the axis at 4 times. That's because it's a fourth degree polynomial. The most that you could have is 4 real roots. You will have 4 roots. Some of them might be imaginary. Here we have an x cubed. This is a cubic equation. You might recall the sum of cubes. Whoa, do you remember that one? Anyway, then you could rewrite this. This second term here, I don't know how to solve it. So I could use the quadratic formula, and I get these two terms. And notice they're conjugates, because these have rational numbers as coefficients. So I have to have both of the conjugates to make it rational. Here I've got a fraction. Well, if I use this x to the cubed is equal to u, then I could rewrite it, factor it, and solve it. To solve a radical equation. So if you have extraneous roots, this is something to watch out for. If you let x equal to u equal to the square root of x, then I can rewrite this as a quadratic, solve it, and end up with it can't equal to -1. I would get u is equal to 7 or a -1. You can't have the square root of x equal to a -1. That's going to be imaginary root. It's not going to work. You can't have the square root of -1. So it will not work in the original equation. It's not that it's imaginary roots, it won't work in this original equation. So bottom line is there's a lot of ways to solve the polynomial equations, and substituting using quadratics, making it into a quadratic and then solving the quadratic is the first thing that you might want to look for if you were going to solve for the solutions of a polynomial. Now I'm going to show you about binomials. If a binomial is a factor, we're going to use synthetic division. There's a video online posted where it shows you how to do this. I will walk it through in the example that we do down below. Synthetic is a shorthand way of doing long division using polynomials and finding the root, finding the solutions. We use it to evaluate a function when it's called synthetic substitution. It's a convenient way to find a function. All right. We do this because of the remainder theorem. What the remainder theorem says is if you want to find the value of f of x, only it's not f of x. If you wanted to find the value of 2 when x is 2, you could substitute it into the equation like I do here. Substitute it in, you find that as 16. But if you were to plug it in, the remainder is going to be my value at 2. It's going to be what this is equal to. So if I were to divide this, if I were to solve this and find the remainder when my x value is, say, 2, for instance, I could do that. So one way to do it is to plug it in. Now this works fine if you're working with just x squared, and you could do this relatively quickly. If you're doing it with the large polynomials, synthetic division makes it really, really a lot of sense. If you did it with long division, this is what it would look like. Now I'm going to show you how synthetic division works. I'm going to take the coefficients of my polynomial. Coefficients of the a squared are 4. The coefficient of the a is -3, and the constant is 6. So these are the numbers that you're dividing. That's what I've written right here. And I'm going to divide it by 2. Why 2? Because a minus 2 is a factor. So 2 would be one of the roots. When we do this, I'll bring down my first number, which is 4. 2 times 4 is 8. 3 plus negative 3 plus 8 is 5. 2 times 5 is 10. When I add these together, I get 16. Now, when you started off, we had an a squared, and I divided it by a. So this is going to be a. This is going to be a constant, and this is going to be the remainder. And the remainder is my a minus 2. It's going to be my what I'm dividing by. Well, I'm dividing by 2 here. It's going to be this factor that I'm dividing by. So this is going to be my remainder, 16. And 16 is the value that you get when you plug in 2. And that's what the remainder theorem says. Bottom line is the remainder is the value of the function at that input. Let's look at another example. Here's one. Notice it doesn't have an x cubed term. If it doesn't have an x cubed term, you need to have a number there representing that. So I have 2. I'm going to put 0 for the x cubed, -5 for the x squared, 8 for the x, and -7. And we're going to divide it by, we want to evaluate it when x is 6. That means that one of our factors is going to be x minus 6. Remember when you do the factors, how they all equal to 0 so that x is equal to 6? So I'm going to plug in 6 here, and I'll put this over to the side. Bring down my first number, because when you divide this factor of 6 into this, the first thing you're going to do is divide it by the number that goes here. This goes to 2 times 6 is 12. This is 12. 12 times 6 is 72. 72 plus a -5 is 67. 67 times 2 is 402. 402 times plus 8 is 410. And 410 times 6 is 2,460. When I add it to -7, I get 2,453. Now, you could have plugged this into the calculator for each one of these numbers here. You could have plugged in 6 for x squared. And when you do that, the f of 6 is equal to, well, it's going to be what the remainder is. It's going to be the 2,453. That's what it is. Doing it with the synthetic division is much easier. And the video that I've posted will help you understand how to do this. And the reason we do it is because it's quicker than plugging in the numbers each time. Special case of the remainder theorem. And this is when you get 0 for your remainder. Well, that means that it's a root or it's a factor. It's a solution. So if I wanted to check to see if something is a solution, I could divide it using synthetic substitution. And if I get 0 as my remainder, whoa, that means that it's a factor. So example, if I want to see if 4 is a solution to this, so x minus 4 would be the factor. So 4 is the solution. I could divide it. Here's my 4. My coefficients are 1, 1, negative 17, negative 20, and 32. I write those down here. Bring down my 1. 1 times 4 is 4. That's 5. 5 times 4 is 20. That's 3. 3 times 4 is 12. 12 subtracted from negative 20 is negative 8. Negative 8 times 4 is negative 32, and I get 0 for the remainder. What this means is that 4 is one of my solutions. It means that x minus 4 is one of the factors. This is really pretty good. Now, I want you to notice, this was x to the 4th, and we're dividing it by x minus 4. So when I divide it with the x term in it, I'm going to get 1, and I'm going to have 1 less x. So this would be 1x cubed, not x to the 4th, x squared, x, a constant, and the remainder. This polynomial that's left over is called a depressed polynomial because we've factored out one of the terms. And you want to eventually factor out all of the terms so that you get all of your answers, all of your solutions. Okay. If there are missing degrees, put a 0 in, just like we did here. Not here. Back here. I had to put in a 0 for the missing term. So if there's a missing term, make sure you put in a 0. Let's see. The solutions of the function were a, b, and c. Then the factors would be x minus a, x minus b, x minus c. The x-intercepts would be, they would occur at, this should be a positive. The x-intercepts would be at positive a, 0, positive b, 0, and positive c, 0. I'll change that in the notes. Zeros aren't always easy to find. So this has limitations. Desmos is a big help, but Desmos won't help you with the imaginary roots. And the imaginary ones, we want to find all the solutions. So we're going to go on. This is where we come to the part of looking at a polynomial to know the number of roots, the type of roots, and where the graph crosses the x-axis. These three things are what we're trying to get at. The fundamental theorem of algebra. This is what it says. And what it means is that for every, if you have a polynomial of n degrees, it's going to have n roots. And this is important. So if it has 4, it's a 4th degree polynomial, it's going to have 4 roots. If it's a 5th degree polynomial, it's going to have 5 roots. Some of them are complex. Some of them may be real. Some of them may be imaginary. So, and also some of them may be double. So if you have x minus 2 and x minus 2 as 2 factors, this would mean that it counts as 2 roots. It will count x is equal to 2 twice as a root. And what that looks like is on a graph, you may have the curve come down and it'll touch the graph and then turn around. So instead of going around and touching it twice like this, it's going to touch it at one point, so it's called a double root. Oh, and another thing. This rule of signs, this is kind of important. It tells us how many number of roots, the type of roots, and the number of zeros where it crosses the x-axis. Now I'm going to show you an example of how this works, and you can read through it slower on your own time. But here we have a polynomial, and I want to know how many positive real roots does it have, or could it have? How many positive negative real roots does it have, or could it have? And how many imaginary roots or zeros would it have? So we took a positive value of x. Here's a change of sign. This is yes, it changes the sign. Going from here to here, no, it doesn't change the sign. From here to here, yes, it changes the sign. And from this to positive, yes, it changes the sign. And it changes the sign again. It changed the sign 4 times. So you could have 4 real roots, or 2, or 0. Notice it goes up by 2's. Here we have No, it doesn't change. It changes once at this point, and it doesn't change again. You are going to have one real root that is negative. No matter how you change it, you're going to have one real root that's negative. And imaginary roots, it's going to be 2, 0, 2, or 4. You have to have a total of 5, and you have to have an even number of imaginary roots. And we'll talk about that in just a second. But think about this. Why is it either 0, 2, or 4? Let's look at the graph. This is a fifth degree polynomial. Its leading coefficient is positive. If I started at the bottom, I could go like this. 1, 2. It would have 1 root, 2 roots, 3 roots, 4 roots, 5 roots. I could have 1 negative and 4 positive. It could go like this, and I don't know how it goes, but it could go 1 root, 2 root, 3 root, 4 root, 5 root. It could have 2 imaginary roots. So there'd be, or it could be, it's going to cross the graph once at least, 2, 3, 4. So you see why this is? So here's an example where we determine not only the number of roots, but what the zeros are. And in this one, we say, well, let's see, it changes the sign one. Oh, I forgot to show you one. Yeah. So it changes the sign once, yes. Twice, yes. 3 times, yes. So you're going to have positive real roots. You could have 3 positive real roots. 3 changes the sign. So it has either 3 or 1 positive real roots. Going from negative to negative to negative, if I plug in a negative value of x, I would have a negative x cubed, then a minus, and this is going to be the same sign. It's going to be negative. Minus, this would be a, let's see, what are we doing here? When you substitute in a negative value here, it says here, since there are no sign changes, that has no negative real roots. So f of x either has 3 real roots or 1 real root and 2 imaginary roots. To find these roots, we can list some possibilities and then we can eliminate them. So you could go through and substitute in here, and oh, there's a root because my remainder is 0. So I know that this is going to be one of my roots, and these are not real roots. And then I would substitute that back in and try to solve for the others. I would use the quadratic formula, and I come up with 1 plus or minus I. So my roots are 1 plus I and 1 minus I. Notice you have to have a conjugate. Now, why do you have to have a conjugate? Well, let's talk about this. The conjugate theorem, complex conjugate theorem says if it has real coefficients in your polynomial, then this has got to be, if this is imaginary number is one of the roots, it has to have its conjugate as a root also. And you think about that. Why would that have to be? Well, it's got real coefficients. If it had only one imaginary root, then it would not have it would have imaginary coefficients as well. So it's got to have real. So here's an example where you write a polynomial with the least degree. So we're going to write the smallest one that we can, using that has coefficients with zeros of 3, 2, 3, and 2 minus I. This is an excellent example. You have a couple of questions like this in your homework, so you want to read this carefully. If this is a 0, then this must also be a 0. These are the conjugates. Notice I have, if this is a 0, that means that 2 minus I is equal to x. So 0 is equal to x minus 2 minus I. If I have 2 plus x, 2 plus I is equal to x, then I have 0 is equal to x minus 2 plus I. So these are my roots. I mean, my factors. When you write the factors out, you have the 1 factor, the 2 factors, and the 3 factors, and you work it out. And you end up with all of the coefficients of this polynomial are real numbers, even though it has imaginary roots. So the bottom line, we're going to solve polynomials to find out what its roots are or its solutions are. And the number of solutions that you will have is the same as the degree of the polynomial. For polynomials with real coefficients, every imaginary root has a second root. And you can use the rule of signs to figure out how many roots are positive and negative. And I'm going to give you another video where we'll actually go through a few of these, but this is enough of a lecture for now. Thanks for watching.